My last two lectures are on a quite different topic. The goal will be to provide an introduction to global properties of general relativity. So we'll answer questions such as the following. Why is a singularity, or in what sense is a singularity inevitable once there's a trapped surface in spacetime? Why can the area of a classical black hole only increase? Why can't you traverse a wormhole in spacetime, at least at the classical level? And why is the ADS-CFT correspondence compatible with causality? So these are mostly statements about the causal nature of spacetime. Where can you get from a given starting point along a world line that's everywhere inside the local light cone? So the causal structure is really what's new in Lorentz Signature compared to Euclidean signature, which is more visible in everyday life. Since our everyday experience is non-relativistic, we're all quite familiar with Euclidean geometry in 2 or 3 dimensions. And curvature is easy to visualize, at least in 2 space dimensions. But what's new in Lorentz Signature is the notion of causality and the constraint to travel inside the light cone. So that's the implications of this is basically what the 2 lectures are about. Now, some of you are familiar with these topics, but some not. And if you're not familiar, I can offer some good news. There are a lot of things you can learn based on only a very small number of ideas. So after a very short time, you too can be an expert, or at least a reasonable facsimile of an expert. So since the questions are about causal structure, we'll be studying causal paths in spacetime. A causal path, x mu of tau, where x mu are coordinates and tau is a parameter along the path, is one whose tangent vector, dx mu d tau, is everywhere time-like or null. And by convention, we'll normally take our time-like paths to be future-directed. So normally, dx mu d tau will be a future-directed time-like or null vector. So geodesics will be important because a lot of questions have to do with what's the best you can do with the causal path. For instance, what's the closest you can come to escaping from the black hole or traversing the wormhole? The answer to such a question usually involves a geodesic with special properties. So we'll start by just considering causal paths in Minkowski spacetime from a point Q to a point P in its future. So here's what's called the causal diamonds of the points Q and P, all points that are to the future of Q and to the past of P. So a causal path from Q to P will stay inside that causal diamond. I'll write dQP for the causal diamond, and it contains all causal paths from Q to P. So the first essential point is that the space of causal paths from Q to P is compact. Now here causality is completely essential. If we dropped causality, we would not have any compactness. Without it, a sequence of paths could oscillate more and more wildly and have no convergent subsequence. So for example, in 2-dimensional Minkowski space, here's a sequence of non-causal paths that go from the origin to the point 1, 0. Let x be the sign of pi n t, where t goes from 0 to 1. Then x oscillates wildly while t is going from 0 to 1. So this is a wildly oscillating sequence of paths with no convergent subsequence. So the space of paths in Minkowski space between 2 points with no causality condition would be hopelessly non-compact. But causality changes things, because in this picture, a causal path can't have an angle of more than pi over 4 from the vertical. Now, we're really interested in causal paths in the Lorentz signature metric, but it's convenient to introduce the Euclidean signature metric with plus signs. And let's ask what a causal path looks like in the Euclidean signature metric. Well, a straight line has Euclidean length 1 between these 2 points, but an arbitrary causal path has length no more than square root of 2. because the condition that the angle is never more than 45 degrees from the vertical ensures that the longest Euclidean path would actually, that's causal, would go like this. And its length would be the square root of 2. It's not unique, but it's an example of the longest causal path. Once you have an upper bound on the Euclidean length, compactness follows. If you have any causal path of length at most square root of 2, parameterize it by a parameter s that measures the length times the arc length, so s runs from 0 to 1. And suppose we're given a sequence of paths parameterized in this way. So x is now the pair t and x. So x is the pair of space-time coordinates. So we consider a sequence of parameterized paths. For each n equals 1, 2, 3, we have a path where x and t, which I've abbreviated as x, depends on a parameter s that runs from 0 to 1. And s parameterizes arc length times a factor that's at most square root of 2. So since the total Euclidean length is square root of 2, even if we forget causality, these paths would lie in a bounded subset. But actually we know they're in the causal diamonds. They start at q and they end at p. So xn of s is independent of s if s is 0 or 1. To get a convergent sequence takes an argument that you probably learned as undergraduates. Let's first set s equals a half. Since xn at s equals a half lies in a compact subset of Minkowski space, there's a subsequence of these paths such that xn of 1/2 converges. Throw away all the other paths and just look at this subsequence. You take a further subsequence where xn of 1/4 and xn of 3/4 converge. And then you do it at fractions whose denominator is 8, and then 16, and so on. So continuing, you get a subsequence that converges at any point of the form a over 2 to the k, with integers a and k. If our paths weren't causal, this actually wouldn't prove anything, because they could oscillate wildly between neighboring integers of this kind. But causality, or the constraint on length, prevents wild fluctuations. So actually, for this sequence, xn of s converges for all s. So we've learned that the space of causal paths between 2 points in Minkowski space is compact.
Can you state briefly what the topology is?
Well, the topology is the one I used in the argument. So what we proved was that we found a subsequence where for every s there was convergence. So
it's like an L1 kind of.
Well, well, if you want to define a topology, it's the topology where an open set is determined by constraint on where you are at finite number of values of s. So those are the open sets. And we found a subsequence which is thank you. We found a subsequence which converges in that topology. I was hoping to avoid answering that kind of question. I'm toying with, well, okay. In a written version, I might define the topology in a footnote, but I was hoping to keep away from it. So the space of causal paths is compact. There's a question that's conjugate to your question, which you might ask later. We'll see if somebody does. Now, a corollary is there must be a causal path from Q to P that maximizes the elapsed proper time, which is given by this usual formula. Well, there has to show that more carefully, there has to be an upper bound on tau, because a sequence of paths whose proper time keeps increasing couldn't have a convergent subsequence. Moreover, if tau 0 is the least upper bound on tau, you could consider a sequence of paths where tau n converges to tau, and that would have a convergent subsequence, which would be a causal path of proper time tau. So,
that would require the C1 conversion.
So you talk about upper semi-continuity, but I'd prefer to avoid it. So what's being said is that I have treated the proper time as a continuous function. It's actually what's called upper semi-continuous, which means it can jump in one direction only when you take a limit. And the direction in which it can jump is such that this argument works. In the particular case of Minkowski spacetime, you can prove this more trivially. There's a unique geodesic from Q to P, namely a straight line, and it's the path of maximum proper time. But the only fact we really needed about Minkowski space to establish the compactness of the space of causal paths was that the causal diamond of points that such a path can visit is compact. Once we know that, once one has that, essentially the same argument would work in any spacetime. So the space of causal paths is compact whenever the causal diamond itself is compact, by essentially the same argument. If the causal diamond isn't compact, the space of causal paths won't be compact, and in general, there won't be a path of greatest proper time. So I'm going to give a trivial example for this and also a more interesting example. Here's the trivial example. You take Minkowski space but remove a point from it. It's still a space-time with a Lorentz signature metric that solves the Einstein equations. So if you discuss arbitrary Lorentz signature metrics that satisfy the Einstein equations, this is one. But obviously the causal diamond is now not compact because we removed a point. And a sequence of causal paths that don't pass through this point, but that converge to one that does pass through it, will obviously not have a limit in the space-time in which we've removed that point. So a point has been emitted, so a sequence of causal paths will no longer have a limit. And if you have 2 points whose geodesic in Minkowski space passes through R, then those will be 2 points that aren't connected by a path of greatest proper time. They're not connected by a geodesic. So there's a more interesting example provided by anti-de Sitter space, but to describe it completely requires some familiarity with anti-de Sitter space. So I'll try to put the minimum requirements on your familiarity. So here I've sketched anti-de Sitter space in 2 dimensions, but in more than 2 dimensions, if you fold over the picture and identify the left and right halves, you'd get the Penrose diagram of anti-de Sitter space in any dimension. So I'll describe it as if we're in 2 dimensions, but you can think of it in any dimension. The left and right-hand boundaries are at spatial infinity. If you try to get to the boundary along a spatial path, its length is infinite. So the boundaries are not part of the space-time. However, if you try to get from the boundary to infinity along a light-like path, you can get there, well, proper time doesn't make sense, but you can get there with finite affine parameter. But what's perhaps most important is that you can get to infinity and back in finite time. So starting at Q, you could go to infinity and back in a finite time. That means that the causal diamond of the point Q and Q prime is not compact, because the points R and S are missing from the causal diamond. But if you replace Q prime with a point a little bit in its past, then from Q to that point, you can't get there by going to infinity and back. So there would be a causal diamond that's compact. So any points to the past of Q prime, say here, from what I've said, has to be connected to Q by a causal path of maximal proper time, and that will be a time-like geodesic. So I've drawn the time-like geodesics from Q. And they fill out this quadrilateral. The points in the interior of that quadrilateral are exactly the points whose causal diamond with Q is compact, because you can't get to infinity and back in a finite time. I can't, okay. And these points are all on a unique time-like geodesic from Q, and those time-like geodesics maximize the proper time. So if you're inside, in the interior anywhere, of this quadrilateral, you're connected to Q by a compact causal diamond and by a causal path that maximizes the proper time. Once you're outside the quadrilateral, there's no compact causal diamond and no general proof that there has to be a path that maximizes the proper time. And indeed, there isn't. So you could be outside the diamond here or maybe up here. And later we'll discuss what happens up here, but at the moment, suppose you're at the point P. First of all, there's actually no geodesic from Q to P. The time-like geodesics do what I've drawn and don't get to P, and the light-like geodesics just go out here, and the space-like geodesics go sideways. So there's absolutely no geodesic from Q to P, and there's no path that maximizes the proper time. The upper bound on the proper time from Q to P is infinity, because a causal path can go very, very close to the boundary, stay there for a while, and then go up to P, always at an angle less than 45 degrees. And because you can be arbitrarily close to the boundary, and because the lengths and times blow up near the boundary, a causal path from Q to P can have an unbounded proper time, arbitrarily large. So this is a more interesting example of the statement that once the causal diamond is not compact, a causal path from Q to some other point P in its future may not exist that maximizes the proper time. To recapitulate, we're studying causal paths because they're the key to understanding black holes, singularities, and all that. And we've learned that the space of causal paths from a point Q to a point P in its future is compact as long as the causal diamond is compact. We'd like a useful criterion that ensures this. Luckily, there's a good criterion that's very well motivated physically. We ask for the space-time M to be globally hyperbolic. Well, what globally hyperbolic means is that it has an initial value surface C, and whatever happens in M can be determined from initial conditions on C. So here's M, and C is some sort of complete space-like hypersurface, which has the property that physics throughout M is determined by what happens on C. So technically, C is space-like. Every point in M that's not on C is in its past or future. That means it can be reached from C by a time-like or future or past-going path. And there's a technical statement that needs a little more explanation. If P is a point to the future of C, then any past-going path from P can be continued till it meets C. And conversely, if Q is in the past of C, a similar statement holds. So the intuition to make physics determinable from what there was on C, it must be the case that any signal you get at P must have somehow came from C. Well, how did a signal get to P? It got to P on some causal path. So to be able to predict the physics at P based on what there was at C, roughly what you need to know is that every causal path started on C. Or to be more precise, as in this technical statement, every causal path can be continued until it reaches C. So if you want to know what signal reached P, well, it was a sum of signals on different paths. And if you know why something came this way, well, it started on C farther back, or maybe it started somewhere else on C farther back. But whatever path by which a signal arrived at P can be traced back till it ultimately came from C. That's meant to be the intuition, and the technical statement that matches the intuition was in this sentence. So informally, if you were missing a point P between P and C, a past-going causal path could get stuck and couldn't be continued until it reaches C. So here that's meant to be a little hole, a point emitted from the space-time. And here there's a signal that can reach P that has nothing to do with what there was on C. In this space-time, initial data at C is not enough to predict what you'll see at P. You need to know what signal arises from the missing points. I think I have another version of the same picture. If there's a missing point, you can't predict what happens in the future without knowing some conditions there. So initial data on C would predict what happens in the white region, but would leave you not knowing what happens in the gray region. So conversely, a space-time that develops from an initial value surface in a deterministic way doesn't have anything missing. So it's not totally clear that only globally hyperbolic spacetimes should be considered in general relativity. For instance, there are lots of analytically continued solutions in all the textbooks that can be continued until they aren't globally hyperbolic. But these are the spacetimes that match the traditional idea of predicting the future and the present from the past. So any alternatives to globally hyperbolic spacetimes are going to be more exotic. So it's at least well motivated to consider this class of spacetimes. And that's the class that we'll be studying in these lectures. Globally hyperbolic spacetimes have the property that spaces of causal paths with suitable conditions on their endpoints are always compact, just as in Minkowski space. So roughly it's because globally hyperbolic means there's no missing point. I'll give an example, though, that's slightly different from what we've said. Here we'll consider the space of causal paths from a point Q to the initial value surface C. I think I didn't introduce the terminology. C is an initial value surface or a Cauchy hypersurface. So I claim, so here's a point Q which is in the past of the initial value surface. And I've drawn only the part that can be reached causally from Q. And I claim the space of causal paths from Q to C is compact. So I'll explain the beginning of the argument. You look at a sequence of such paths. You want to show it has a convergent subsequence. Well, to begin the argument, inside the future of Q, there's a small piece that looks like a causal diamond in Minkowski spacetime. And we already know that restricted to that small piece, the space of causal paths is compact. So our sequence has a subsequence that converges at least inside this little bit. So it converges as far as Q prime. And then we start again at Q prime and continue in the same way and get a subsequence that converges farther. And then we keep going and we learn that a subsequence converges all the way up to C. So global hyperbolicity ensures that we can always continue. It ensures that whenever we've found a partial convergence to a partial causal path, first it ensures that that partial causal path can be continued, and then you repeat the arguments, basically. So you eventually learn that the space of causal paths from Q to C is compact. In particular, the region of space-time that such a path can visit is compact. Obviously, if there were a sequence of points that can be visited by causal paths from Q, and that sequence had no convergent subsequence, then a sequence of paths that visit those points would also have no convergent subsequence. So if M is globally hyperbolic, the portion of space-time that can be reached by paths from Q to C, causal paths, is compact. The gray region is compact. Now here's an exercise, but it's a little harder than most of the exercises I've asked. Using what I've explained, show that in a globally hyperbolic spacetime, if P can be reached by a causal path from Q, then the space of all causal paths from Q to P is compact. If you want to do it, let me suggest that you take Q to be in the past of M and consider separately the cases that P is in the past or the future. Sorry. Take Q to be in the past of C, the initial value surface. Use as a lemma what I explained here, this statement. And then consider separately the cases that P is in the past or the future of the initial value surface. You'll need two different arguments in the two cases. But if you understood the claim about causal paths from Q to C, you should be able to deduce a similar statement about causal paths from Q to P for any point P in the future of Q. So this exercise means that globally hyperbolic spacetimes have the property that spaces of causal paths between 2 points are always compact. Now compactness, okay, you haven't done this exercise and you may need to think about this argument more. But let's accept that in a globally hyperbolic spacetime, which means a spacetime where you can predict the future from the past so that nothing is missing, that spaces of causal paths are compact? Well, if so, it means that there's a causal path of maximal proper time from any point Q to any given initial value surface C, and also to any other point P in its future. Now, what I want to do from here is to navigate to the non-trivial result about singularities that's easiest to explain. That means not following the historical order. The historical order involved first a result of Penrose that we'll probably not come to till tomorrow. The easiest result to explain is Hawking's theorem about the Big Bang in traditional cosmology without inflation. It's easier to explain because it only involves time-like geodesics, but the other applications involve the slightly more subtle case of null geodesics. So before we get to time-like geodesics, we're going to work in ordinary Riemannian geometry where we all have more intuition, or at least most of us. Then we'll go over to the Lorentz signature case. So here's the question. In Riemannian geometry, is the geodesic the shortest distance between 2 points, the shortest path between 2 points? Yes, for a short enough geodesic, but in general, no for a geodesic that goes too far. A geodesic extremizes the length but may not minimize it. Here's a picture on a two-sphere. If P and Q are close enough, then there's a unique shortest geodesic between them. A geodesic that goes less than halfway around the sphere is the unique shortest path between those 2 points. But a geodesic that leaves Q and goes halfway around the sphere arrives at what's called a focal point, Q prime, also called a caustic, on the other side of the sphere. For instance, if Q is the North Pole, then every geodesic from Q will meet at the South Pole. The South Pole is a focal point for all the geodesics from Q. And the South Pole is halfway around the sphere from the North Pole. So this point should have been labeled as Q prime, not P, Q. It's meant to be the focal point that's supposed to be halfway around the sphere. I don't think the drawing shows that well. And what's meant to be shown is that if P is well, I had a problem, which is that if you can see Q, then you can't see the focal point. It's on the other side. And I wasn't a good enough artist to deal with that. But what I wanted to show in the picture is that if P is halfway around the sphere, there are many geodesics that are shortest geodesics, not just one. And that's because all the geodesics from Q focus at the focal point on the other side. So a geodesic continued past the focal point is no longer the shortest path because you can do better by slipping the path around the sphere. In the case of the sphere, you all know this. You start at the North Pole, go around to the South Pole, and keep going. You've gotten there by a geodesic, but a shorter geodesic would have gone the other way around. So in general, if you continue a geodesic past a focal point, it's no longer the shortest path. And that's in general true. Suppose that QP is a geodesic that has a focal point Q prime. Having a focal point Q prime means that the QQ prime segment can be deformed to this segment that's also a geodesic. So the QQ prime part of the geodesic can be slightly displaced to a nearby geodesic that connects the same 2 points. Well, the displaced geodesic has the same length as the first one, since geodesics are stationary points of the length function. So if you can displace a geodesic that, with keeping fixed the endpoints, that doesn't change the length. But the displaced geodesic has a kink, and its length could be reduced by rounding out the kink. So if there's a focal point, Q prime, between Q and P, by replacing this segment with this one, and then smoothing out the kink, you'd get a shorter path from Q to P, showing that a geodesic that's been continued past a focal point never minimizes the length between the 2 points. Any questions about that? So in this case, we learned that the original geodesic was not length minimizing. Now, it's not important that all geodesics from Q are focused to Q prime, which is what happens in the case of a sphere. All we used in the argument was that there was some direction in which the QQ prime segment could be displaced, not changing its endpoints. And we didn't even need to know that the QQ prime geodesic can be displaced exactly as a geodesic. All we really need to know is that it can be displaced while solving the geodesic equation in first order. In other words, we needed to know that the equation for deforming a geodesic has a zero, for deforming the geodesic, keeping its endpoints fixed, we need to know that it has a zero mode, so that to first order, we can solve the geodesic equation by some displaced thing. If that happens, since we solve the equations to first order, the displacement doesn't change the length function in second order. But rounding off the kink does reduce the length in second order. So displacing the QQ prime segment and rounding off the kink will reduce the length if the displacement caused no increase in second order, or in other words, if the displacement came from a zero mode of the linearized equations, not necessarily an exact displacement that you can make to all orders. So, any questions? Now, often we want something similar, but not concerning a path from a point Q to a point P, but from some initial set W to P. So the simplest case is that W is a submanifold. And, well, you basically all know how to try to find the shortest path from a submanifold to P. It should be a geodesic that's orthogonal to W. It should be a geodesic that connects W to P, but where it leaves W, it should be orthogonal to W. If it left W as an angle, at an angle like this one, you could shorten it by moving the point where it leaves closer in the right direction so that it became orthogonal. Now, just as before, if P is close enough to W, an orthogonal geodesic from W to P minimizes the length among paths from W to P. But if you continue past the focal point, the geodesic stops being length minimizing. Same story. Well, I have to say what a focal point is. A focal point is a point Q prime such on the geodesic from W to P, such that this segment can be deformed to the green segment, which is supposed to be another nearby geodesic also orthogonal to W. So that's a focal point. This is a focal point if this segment can be deformed to a nearby segment that's also an orthogonal geodesic from W to P. So the reasoning showing that a geodesic with a focal point isn't length minimizing is the same as before. Displacing this segment to the green one doesn't change the length, and rounding off the kink reduces the length. So this is your last chance to ask a question about Euclidean signature. Yes?
You talked about that deforming these curves.
Yeah.
Do that smoothly? It seems we can remove a point and still be able to...
Well, we're not removing points. No, sorry. A geodesic is a continuous curve in spacetime, right? So we don't remove a point from it. A geodesic solves the differential equation.
I mean, if we were to remove a point between these two geodesics that you sketched, the blue and the green, then this argument would still hold. So does our deformation need to be a continuous deformation between geodesics?
Well, the argument is based on making the deformation from the okay, I'll take the question to be reiterate what kind of deformation we want. We have the blue curve, which is a geodesic that's also orthogonal. That means it solves a certain differential equation. We find a zero mode of the differential equation, meaning that to first order we can make a displacement. I've drawn the picture with the finite displacement because it's the only picture I can draw. But in your mind's eye, in this argument, you make a very, very slight displacement of the blue one to a nearby green one. And the displacement, so now we have a path from W to P, which has the same length as before, but it's not a geodesic. It has the same length because we deformed from here to here, still solving the geodesic equation. Since geodesics are critical points of the length function, any family of geodesics between given endpoints, or in this case, one endpoint fixed and the orthogonality condition, such family of geodesics have the same length. So trading in this blue part for that green part doesn't change the length. or it doesn't change length up to and including second order if we only solve the zero-mode equation in first order. So we've gotten this non-geodesic path from W to P that has the same length as the geodesic. But because it's a non-geodesic path, it can be improved by rounding out the kink. And that will make a shorter path from W to P. So a geodesic orthogonal to W that's continued past the focal points does not minimize the length anymore. So I'll invite one more question on Euclidean signature. Yes?
So in the example of the sphere, we go to Q prime and then go back. So this will be the rounding? It's a bit, how do you describe
I think you should see it for yourself. So go from the North Pole on a geodesic to the South Pole and keep going.
But the other one,
Now replace the geodesic part from the North Pole to the South Pole by a geodesic that went sideways from the North Pole to the South Pole. Now you've got a path that went from the North Pole to the South Pole, and then it went off at a right angle or something.
right.
Now, I hope you can visualize spherical geometry well enough that you can see it's got a kink, and if I round out the kink, I make it shorter.
Right. Okay. So you do it. I thought you do it straight. Like, okay. Do it.
Well, the point of the argument is that in the case of the sphere, you know what the whole sphere is. But if we're making general arguments about Riemannian geometry or general relativity, we want to use only what we know for sure, which is the behavior near the geodesic. And the reason I emphasize slightly rounding it out is not that that gives the shortest path, but it's enough to prove that the original one wasn't the shortest. And it only used the geometry near the original path. So in the arguments we'll present, well, eventually Hawking and Penrose tried to prove statements about the global geometry of spacetime, but you start with much less knowledge. So it's important to make an argument about improving your geodesic that only uses the geometry near that geodesic. I think we have to go on to Lorentz signature, but since the considerations will be similar, if you had a question here, you'll get another chance. Well, I see one more. I'll take a quick question.
If the spacetime has a boundary,
No, we're not discussing spacetimes without boundaries. Our spacetimes are manifolds with Lorentz signature that satisfy the Einstein equations. So now we go over to Lorentz signature. But what we've said has no good analog for space-like geodesics. A space-like geodesic will never be a minimum or a maximum of the length function because oscillations in spatial directions tend to increase the length and oscillations in time directions tend to reduce it. So 2 points at space-like separation can be separated by an arbitrary by a space-like path that's arbitrarily short. In this picture, a time-like path is at a 45-degree angle. This path goes almost at a 45-degree angle and then goes back. It's a space-like path, but it's almost time-like, so it's very short. And I think you all know, I use the time direction, but even without using the time direction, by wiggling in space directions, you could make a very long path between 2 points. So there's no upper or lower bound on the length of a space-like path between 2 points. But what happened in Euclidean signature has a beautiful analog for time-like geodesics. Here we discuss the elapsed proper time along a geodesic, not the length, and spatial fluctuations tend to reduce it. So a sufficiently short segment of any time-like geodesic maximizes the elapsed proper time. But if you continue a time-like geodesic past a focal point, it no longer maximizes the proper time. So the blue is meant to be a time-like geodesic from P to Q. But a focal point means that there's some point Q prime such that there's another nearby time-like geodesic, the red one, which I hope you can see, that reaches the same destination from Q that the blue one reaches. So that means if the QP geodesic contains a focal point, it can be replaced with a non-geodesic time-like path that has the same proper time. Since it's not a geodesic, you could again round it out. And while rounding it out reduce the length in Euclidean signature, it increases the proper time in Lorentz signature. The fact that rounding out a time-like path increases the proper time in Lorentz signature is called the twin paradox. So a twin that stays at rest has longer proper time than one that accelerated and then bent back. So I'm using a sufficiently small region where we do the rounding can be approximated by Minkowski space. So the statement that rounding increases the proper time is literally, if you like, the twin paradox at work. So a time-like geodesic that continues past the focal points doesn't maximize the proper time for the same reason that in Euclidean signature, a geodesic that goes past the focal point does not minimize the length. So I'm going to give two examples of time-like geodesics that don't maximize the proper time between their endpoints. And then I'll give you all a chance to complain about this claim. So the first is in the motion of the Earth around the Sun. So if you follow the Earth's motion over many orbits, you get a geodesic that does not maximize the proper time. That's because you could do better by launching a spaceship into space with almost the escape velocity from the solar system. So it goes way, way up, stays there for a long time, and you time its orbit properly so it falls back to Earth. That means while the Earth goes around many orbits, the spaceship goes way out here and then comes back. Well, the proper time that elapsed on the spaceship was longer than the proper time on Earth because the spaceship is less affected both by Lorentz time dilation and the gravitational redshift. So the motion of the Earth around the Sun, when continued for a long enough period, does not maximize the proper time. Now, my second example has the advantage that we can describe a focal point. So the second example is anti-de Sitter spacetime. So we start at the same point Q as before, and as the picture shows, the time-like geodesics that leave Q all reach a focal point at a point Q prime. So this is an analytic continuation of the same fact for a sphere. You all know that a geodesic from the North Pole will focus at the South Pole. Well, anti-de Sitter 2 space is an analytic continuation of the 2 sphere to Lorentz signature. It has the same property that the geodesics from Q all focus at Q prime. Now, previously we considered a point that can't be reached from Q by a time-like geodesic, but now we'll consider a point that can be reached from Q by a time-like geodesic, but that point has gone through a focal point. So the point R is on a time-like geodesic from Q, but that time-like geodesic has gone through a focal point, so it does not maximize the proper time. So what do you think is the maximum proper time for a causal path from Q to R? Okay, so 3 cheers for whoever said infinity, because as in the previous example, you can go out to the boundary. You don't literally go all the way to the boundary, which is infinitely far away, but you go close to the boundary, as close as you want, stay there for a while with no upper bound on the proper time, and then you go back to R. So once we've passed a focal point, the geodesic no longer maximizes the proper time, and in fact, in this example, there is no upper bound on the proper time. In the case of the Earth going around the Sun, there would have been an upper bound on the proper time because that's happening in a globally hyperbolic spacetime. ADS is not globally hyperbolic by the definition we used because there are causal paths, take an initial value surface here. There are causal paths that can't be continued until they reach the initial value surface, namely a causal path that would go this way to the boundary. So ADS is not deterministic in the sense assumed in our lectures because it needs a boundary condition at spatial infinity. So you can modify the statements, you can modify the definition of global hyperbolicity for the ADS case, but it's not globally hyperbolic by the standard definition. And that's part of why there's ultimately no path from Q to R that maximizes the proper time. So I guess this is your good chance to complain about Lorentz signature paths that maximize the proper time. I'm going to assume that was an extremely clear and convincing explanation. Now, in general, focal points are easy to come by because a very slight gravitational attraction can cause geodesics to eventually converge. To prove a singularity theorem, we need a good way to prove that time-like geodesics develop focal points. That's provided by the Ricciardori equation. It's actually provided by Ricciardori's original equation, not the more subtle variant due to Sachs that was introduced later and is nowadays what's most frequently called the Ricciardori equation. So in d dimensions, we'll consider a space-time with an initial value surface S, whose coordinates I'll call x vector. xi runs from I up to little d, which is capital D minus 1. So here's the initial value surface. And by looking at time-like geodesics orthogonal to the surface, we construct a coordinate system in spacetime. So at every point on the surface, we find a time-like geodesic that's orthogonal to the surface. There's a unique one. And every point that's close enough to the surface is on a unique orthogonal time-like geodesic, which will be the path that maximizes the proper time from P to S. So if P is close enough to S, there will be a unique time-like geodesic and it will maximize the proper time. And then we use this to give a coordinate system. If P is on a geodesic that meets S orthogonally at x, and it's a proper time t to the future of x along the geodesic, then we assign to P the coordinates t and x. And these are good coordinates near the surface S. I hope it's obvious they're good coordinates. Locally, the situation is like Minkowski space. In Minkowski space, S could be time 0, and we'd parameterize S by the spatial coordinates x, and the orthogonal geodesics just run in the time direction. And the coordinate system we'd get this way would be a standard Lorentz coordinate system. Now, in this coordinate system, the metric looks like I've written, minus dt squared plus a spatial metric. So I could have described this coordinate system by saying that g00 is minus 1 and g0i are 0. That might have looked like a more familiar way to describe the coordinate system. But the more geometric language of orthogonal geodesics has the advantage of helping us understand how the coordinate system breaks down. If I'd used this language, I'd have just told you that locally we could satisfy that gauge condition, but it might break down if you go too far away from the surface S. And it's important for us to know how it breaks down, and the language of orthogonal geodesics will help us understand that. So even if the space-time doesn't become singular, our coordinate system breaks down at focal points. Because if several orthogonal geodesics from S meet at the point P, then we would not know which coordinates to use for P. A focal point can't be labeled by which orthogonal geodesic it's on, so our coordinate system will be bad when a focal point occurs. And in a weak gravitational field, the way the coordinate system will break down, in a weak geodesic gravitational field that is nowhere near producing a singularity, the coordinate system can still break down at a focal point. So since the spatial metric determines the distance between neighboring geodesics, a sufficient condition for a focal point is that the determinant of the spatial metric goes to 0. Let me just make that clear. So in this metric, the geodesics we're talking about are at fixed x. So no matter what t is, the metric gij measures the difference between parallel orthogonal geodesics from S. But gij depends on t in a way that you find by solving Einstein's equations. So the distances between geodesics are time dependent in general, and a focal point means that some distances go to 0, which means that the determinant of the spatial metric goes to 0. So that'll be our sufficient condition for a focal point. And the Ricciardori equation will give a sufficient condition to ensure that the determinant of g goes to 0 within a known time. The Ricciardori equation is just the 0, 0 component of the Einstein equation. in the coordinate system of the orthogonal geodesics. So we just have to calculate R00, and in this metric, it's that, well, it can be notoriously tricky to, sorry, not tricky, but tedious to calculate the Riemann tensor. But if you try it, you'll find that this is a case where you can do it quite easily. And after a relatively short computation, you'll get this formula for R00. Now, it's customary to define A, or sometimes V, which is the square root of the determinant of G. It measures the area or volume, depending on the space-time dimension, occupied by a little bundle of geodesics. And then A dot over A is a half of the trace of G inverse G dot. It's called the expansion, and it's often denoted theta, but I will really only use that notation in the null case. It's convenient to also define the traceless part of G inverse G dot, which is called the shear. Although people usually, 1/2 of what I call M is the shear. And then the formula for R00 expresses it in terms of A dot over A and the traceless part M. Now, it's convenient to define a modified stress tensor, which is the stress tensor minus 1/2 G mu nu times the trace of the stress tensor. And then the Einstein-Ricciardori equation, which I remind you is just the 0, Einstein equation, becomes this. Now, what's called the strong energy condition is the statement that T00 hat is non-negative at every point and in every local Lorentz frame. So it's satisfied for non-relativistic matter, for radiation, and for a negative cosmological constant. The outstanding example that doesn't satisfy it is a positive cosmological constant. And so, for example, the present universe is believed to not satisfy the strong energy condition because of the cosmological constant. If we assume the strong energy condition, all the terms on the right-hand side of the Einstein-Ricciardori equation are negative. So minus trace m squared is negative. The strong energy condition says that minus T00 hat is negative. So the strong energy condition says that this thing is negative. And a little algebra shows us that d by dt of 1 over A dot over A is bigger than 1 over the spatial dimension. So now we can get a useful condition for the occurrence of focal points. We go back to our initial value surface. We assume that A dot over A is negative at some point on the surface. Say it's equal to minus lambda, where lambda is positive. So the initial value of 1 over A dot over A is minus 1 over lambda. And the inequality on d by dt of 1 over A dot over A implies that it goes from 0 to below within a known time, a known proper time, which is d over lambda. So equivalently, A dot over A goes to minus infinity within a known proper time along the orthogonal geodesic. In other words, the future going orthogonal geodesic leaving S meets it meets a focal point where A goes to 0 or a singularity where A dot goes to infinity within a proper time d over lambda. If you're more careful, you can show it meets a focal point before it meets a possible singularity. I won't actually show that. So this shows that focal points are easy to come by. For example, you could be simply in Minkowski space. If your initial value surface is time 0, the orthogonal geodesics go straight ahead in time and never focus. If you took a wiggly initial value surface, the orthogonal geodesics will meet somewhere in the future or the past, depending on how it wiggles. So a wiggly initial value surface in Minkowski space will lead to a lot of focal points. So in any situation where the gravitational fields are weak, you're going to get focal points, not singularities. So now we're ready for Hawking's theorem about the Big Bang. Hawking assumed the universe is globally hyperbolic with an... Actually, before I present the theorem, I'll stop for questions. So Hawking assumed the universe is globally hyperbolic with initial surface S, and he assumed the strong energy condition. In other words, he assumed the stress tensor was made of ordinary matter and radiation. The inflationary universe had not been invented yet, and it gives a way to avoid Hawking's conclusion because a positive cosmological constant violates the strong energy condition. Well, if the universe is perfectly homogeneous and isotropic, it's ascribed by a well-known cosmological solution of these people, and it emerged from the Big Bang at a calculable time in the past. But suppose more realistically that the initial surface is not perfectly homogeneous, but that the local Hubble constant is everywhere positive. Did such a universe emerge from a Big Bang? One could imagine that as you go back in time, the inhomogeneities become more severe. The standard solution is not a good approximation, and part or most or maybe even all of the universe did not come from an initial singularity. So that's the question that Hawking was addressing in his theorem. He showed that, well, under the assumption of the strong energy condition, there must have been a Big Bang. So, assuming the strong energy condition and that the universe is globally hyperbolic, he showed that there was a Big Bang. To be more exact, he showed that if the local Hubble constant has a positive minimum value h min on an initial value surface S, then no point in space-time is a proper time more than h min to the past of S. I should define precisely the local Hubble constant. For a homogeneous isotropic expansion, like the usual one, where I've avoided spatial curvature for simplicity, partly because it was unimportant in the past, you usually define the Hubble constant by r dot over r. That's the same as a dot over a times d, where a is the determinant of the spatial metric, which is the same as r to the d in this case. So this is the definition we'll use for the local Hubble constant. So our assumption is that a dot over a is equal to or bigger than the spatial dimension times h min, assuming time is measured toward the future. But we're going to measure time toward the past, looking back toward the Big Bang. So we'll write the hypothesis as being that a dot over a is less than minus d times h min. So the proof of Hawking's theorem consists of comparing two statements. Since the universe is globally hyperbolic, every point p to the past of S, well, every point p in general, is connected to S by a causal path of maximal proper time. As we know, such a path is a time-like geodesic without focal points, and it's orthogonal to S as shown. So that was the first statement. The second statement is that the initial value of a dot over a being less than minus dh min implies that any past-going time-like geodesic orthogonal to S develops a focal point within a proper time at most 1 over h min. So if you combine the statements, you see that there's no point in space-time that's to the past of S by a proper time more than 1 over h min. So still assuming the strong energy condition, the minimum value of the local Hubble constant gives an upper bound on how long anything could have existed in the past. That's Hawking's theorem about the Big Bang, or at least the simplest version of it. Any questions about Hawking's theorem or the ingredients that went into it?
How necessary it is to talk only about time-like geodesics?
I can't quite hear, sorry.
How necessary is it to talk about time-like geodesics? Can you talk about accelerated trajectory or something?
A time-like geodesic, I still don't understand the question. Let me come closer, or stand up and speak louder.
So I was asking that how necessary is it to talk about time-like geodesics? Can we think in terms of accelerated trajectory?
Well, okay, the question is whether time-like geodesics are important in those arguments. I don't know what other arguments there might be. So I'm not sure how to answer that question. This argument works very elegantly for globally hyperbolic spacetimes where every point p is connected to the initial value surface by an orthogonal time-like geodesic that maximizes the length, the proper time. I don't know what you could do with non-geodesics. Any other questions on anything up till this point?
How much of GR is needed for this proof? Like if we replace Einstein's equation by some other
Well, the question is, what if we replace Einstein equation with some other equation? There aren't a lot of interesting equations to replace it with. You can add higher curvature terms to Einstein's equations. You'll mess this up a little bit, but in practice, you might want to remember those equations are generally hard to take. Okay, the quick answer is I don't know, because I don't take. Let's see. If the higher terms you add to Einstein's equations have infinitesimal coefficients, then they're not going to do anything. Naively, and I'm not sure it's physically sensible to study such equations when the coefficients are taken to have a big equation, a big effect. But with that said, I don't know the answer to your question. There's a relatively sensible case above 4 dimensions. In 4 dimensions, there really aren't any sensible equations to use instead. Above 4 dimensions, there are some relatively sensible ones. I don't know if anyone has looked at what happens to the Ricciardori equation, so I can't answer the question properly. Any other questions? Yes?
Sorry, could you mention again why this is not just a coordinate singularity?
Let's compare the two statements. The question is, why is this not a coordinate singularity? We compare two statements. The first statement, every point P is connected to S by a causal path of maximal proper time. That was the first statement. The second statement shows that that path of maximal causal time cannot have a length more than 1 over h min. So we've proved that every point is a time no more than 1 over h min to the past. Any other questions? Well, I hope you've all had so much fun that you're now anxious to start studying null geodesics. So any null geodesic has 0 elapsed proper time. But nevertheless, there's a good notion that has similar properties to maximal proper time for time-like paths and minimum length in Euclidean signature. We'll say that a causal path from Q to P is prompt if no causal path from Q to P could have arrived sooner. To be precise, a causal path L from Q to P is prompt if there's no causal path L prime that would have arrived at a point that's near P but to its past. So this path is prompt if you couldn't have gotten there faster. If there's no causal path from Q to R, even if R is only slightly in the past of P, then we say that the path from Q to P was prompt. And prompt causal paths, as you'll see, are very special, but they're analogous to time-like paths that maximize the proper time, or Euclidean paths that minimize the distance. So more or less by definition, it means P must be in the boundary of the causal future of Q. By the causal future J plus of Q, we mean all points that we can reach from Q by a future-going causal path. For instance, in Minkowski spacetime, J plus of Q consists of all points in or on the future light cone. Well, if a point U is inside the future light cone, then a point slightly to its past is also inside the future light cone. From a causal path from Q to someplace inside the future light cone is not prompt. But if I take a point U that's on the future light cone, then slightly to its past you're outside the future light cone. And you can't get there by causal path from Q. So a causal path from Q to a point on the future light cone is going to be prompt. And it's also going to be unique. It'll be a null geodesic.
So what does near mean in the definition of prompt?
Well, you take how do you decide that the point R? The question was, what exactly do I mean by near? I was hoping it was intuitive, but anyway, let's go back. To decide that R is in the past of P, we find a time-like path from R to P. It has a proper time. I could take an arbitrarily small bit of that. So near means that no matter how close we are to P, but slightly to its past, we can't get there from Q by a causal path. So prompt means that P is the absolute best we can do. We can't get even slightly to the past of P by any causal path.
What does sooner mean?
Sooner means along this time-like path. So, what? This was a time-like path. R is strictly in the past of P. So this is a time-like path.
Is it prompt globally with space-time have a different topology or
Juan is asking the tricky question of whether I'm imposing a global or local condition on prompt. So for some applications, it's important to impose a global condition, but for a long time, we'll only be imposing local conditions. I want to explain the local conditions, but I also will remark on the importance of a global condition at some point. So as you can see, if you want to get from Q to U, you can barely get there along a null geodesic. You couldn't have gotten anywhere that's strictly in the past of U. So the null geodesic from Q to U is prompt. And more generally, in Minkowski spacetime, every null geodesic is prompt. And every point on the boundary of the light cone is connected to Q by a prompt null geodesic. So even though prompt causal paths are very exceptional, they are useful analogs of proper time maximizing time-like paths. So we're going to explore their properties. So first of all, a short enough segment of any null geodesic in a Lorentz signature spacetime is prompt, just as if one were in Minkowski spacetime. But if continued, a null geodesic might become non-prompt because of gravitational lensing. Here's an example. Well, recently astronomers saw multiple images of the same supernova. The images did not arrive at the same time. And obviously, the images that did not arrive first were not prompt.
Using the proper time on the geodesic, you're measuring, we're sitting here in some place asking which one will arrive.
Well, in the definition of prompt, well, okay. I'm not sure it will help to give a detailed answer to that question. There are a lot of equivalent notions you could define. I think, okay, clear. The geodesic that arrived 1 year later did not get there as soon as possible. The idea of prompt, you could work out formally by the definition I used before, but let's not do that. So definitely, if you study that example more carefully using Einstein's equations, you can apply all the points that we'll be discussing. So a causal path L whose tangent vector is somewhere time-like rather than null can't be prompt, because by modifying L to be everywhere null, you'd find a nearby causal path that would arrive in the past of P. Sorry. The reason I emphasize nearby is the same as in the answer to a previous question. When we are studying a geodesic and we want to decide if it's prompt, there are some local conditions that we can study just using the geometry near P. And those are near that path. Those are easier to discuss because we at least know about the geometry near that path. There may also be global conditions. I hope you can see, can you see this if I, is it possible to see that? Someone in the back? So if the, okay, let me curve slightly so this is a time-like path. If it's somewhere time-like, then somebody traveling on this path could deviate and go off in a null direction slightly to the past. And once you're slightly to the past, you can keep going everywhere slightly to the past on a causal path. So when I say slightly to the past of given causal path, I mean a causal path that almost follows the first one, but is everywhere slightly to its past. Once you get to the past of another causal path, you can keep going parallel to it and remain always slightly in the past. And if a causal path ever deviates even slightly from being light-like, that means it's not going as fast as it could have gone. You could deviate in the same direction, but in a light-like direction, get slightly in the past of the first one, and once in the past, always in the past. So a prompt causal path will have to be everywhere null. And it actually has to be a null geodesic, because if it bends everywhere, it won't get to its destination as quickly as possible. So this is meant to be a picture in space. So imagine it's actually a Minkowski space. Imagine that these are spatial trajectories, but each particle was traveling at the speed of light. So elapsed time, which isn't drawn, is the same as the elapsed arc length. Since this arc length is bigger, this path arrives later in time than this one. So the one that wasn't a geodesic can't be prompt. I explained that in Minkowski space, but it's automatically true in any spacetime because a small part of any spacetime can be approximated by Minkowski space. And whatever you can do in Minkowski space to get ahead of a non-geodesic causal path, you can do that locally in any spacetime. And once you're slightly ahead, you just stay ahead. You don't know where the causal path is going, but wherever it's going, you follow it, but slightly to its past. So in Minkowski space, when I tell you that a causal path has to be a null geodesic, that a prompt causal path has to be a null geodesic, I'm just saying that to get somewhere as quickly as possible, you should travel in a straight line at the speed of light. But that's actually true in any spacetime in the form that the most prompt causal path is always going to be a null geodesic. Not every null geodesic is prompt, but the promptmost causal path is always a null geodesic. And finally, and you perhaps knew that this was coming, to be prompt, a null geodesic must contain no focal points. So the definition of a focal point is similar to before. Q prime is a focal point if the QQ prime segment of the null geodesic can be slightly displaced to a nearby null geodesic from Q to Q prime. So QP is a null geodesic, but the QQ prime segment can be displaced to another null geodesic nearby, drawn in red. And now we have a path, a causal path, namely the red one followed by the green one, that's null, but it's not a geodesic. And since it's not a geodesic, by rounding out the kink, you could move it into its past. So you'd modify the orbit slightly near this point and get to the past of this green geodesic and stay everywhere to its past. Wherever it goes in space-time, you follow it slightly in its past. So the fact that bending can let you get into the past, well, there's a Lorentz frame in which bending would be bouncing back from a mirror. So up to a Lorentz transformation, the statement is that a light ray that bounces off a mirror wasn't prompt because while the light ray went this way and that way, you could have just stayed at rest and then gone off at the speed of light earlier. So if you can deform, if there's a focal point in the QP geodesic, by deforming it and then rounding off the corner, you get a nearby causal path that's time-like near the corner. And since it's time-like near the corner, a further modification would put you strictly in the past of the green segment between Q prime and P. So any questions about that? Yes?
Yeah, so would these like prompt paths like minimize like the affine length analogy?
Well, the question is if prompt paths minimize the affine length. It's a good question, but you have to remember that there's no natural normalization of the affine parameter. So there isn't a well-defined function you'd want to minimize. In Minkowski space, if you have 2 points null separated, there's no natural measure of the distance between them. Because up to a Lorentz Poincare transformation, any 2 null separated points can be mapped to any other 2. So there can't be a natural measure of distance along null geodesics. So we don't minimize any, we don't say we're minimizing or maximizing anything. Instead, we say there's no focal point. The reason I started in Riemannian signature and then discussed time-like paths was so you'd be familiar with focal points as a good criterion. And when we get to null paths, which are the most important one, they don't minimize or maximize anything, but the existence of a focal point is a good substitute for saying that a path is not optimal, not prompt. Another question, if there is one.
Is the absence of focal points sufficient for a null trajectory?
No, that's actually, the question is, if I've stated this as a necessary condition for a null, for promptness, it's not a sufficient condition. Juan also asked the same question basically a few minutes ago. There are easy counterexamples, and I'll eventually give a counterexample. So we're only discussing necessary conditions for promptness, not... Oh, well, I might in a moment tautologically state a sufficient condition, but anyway, so far only necessary conditions. Likewise, we say a path from a set W to a point P is prompt if it arrives as soon as possible in the same sense, meaning you couldn't have arrived slightly in the past of P. So L is prompt if there's no path that would have arrived slightly before P. So the same arguments show that a causal path to be prompt has to be a null geodesic. And very, very importantly, if W is a submanifold, then in addition, L has to be orthogonal to W. The argument for that last statement is very important, but the argument for it is the same as it was in the Euclidean case if you saw it in high school. If L is not orthogonal to W, first of all, I should tell you what orthogonality means, just to make sure that isn't confusing. Orthogonality means that any tangent vector to W at the intersection point is orthogonal in the Lorentz metric to the tangent vector to L. Same definition that orthogonality usually has, but except we're in Lorentz signature. If L is not orthogonal to W, if L leaves W at an angle, this is W and this is L. If L leaves W at an angle, then by moving the starting point closer to orthogonality, in Euclidean signature you would reduce the length, but in Lorentz signature you could move L into the past. So to be prompt, L has to be orthogonal to W. Orthogonality between a null vector and a space-like set is only possible if W has real codimension at least 2. And that case will be very important. You see, if the codimension... Okay. So a prompt path, to be prompt, a path from L to W must again have no focal point, where the definition of a focal point is similar to what it was before. The blue geodesic has a focal point at Q if this segment can be deformed to a nearby null geodesic that's also orthogonal to W. And the proof is the same as before, if you can make such a deformation. Then by rounding out the kink and using the twin paradox or the mirror reflection principle or whatever, you could find a causal path that would have arrived in the past of P. Now, in a general globally hyperbolic space-time, such as maybe the whole universe, the real universe, a null geodesic can develop a focal point because of gravitational lensing, so not every null geodesic is prompt. If you want to find an example, first look in your telescope and see a gravitational lens. Okay. Whenever there's a gravitational lens and 2 images, they arrive at different directions and different times. But if you could move around in 3 dimensions at in your spaceship, you could find a point where those 2 geodesics would meet, and that would be the focal point. In other words, the fact that the rays were focused were bent by a gravitational lens will tell you that there's going to be a focal point somewhere. Sorry, that was too much of a digression. So, a null geodesic might develop a focal point, but there's an important fact that's true just as in Minkowski space. Every point in the boundary of the future of a set Q, the boundary of the causal future of Q, is connected to Q by a prompt null geodesic. That's actually true for any set W, any space like set W. So here's the proof. So W is any set, and J plus of W is its causal future. J plus of W consists of all points you can reach from W by a causal path. So the P's are some examples of points in J plus of W, and the red curves are causal paths from W. U is a point on the boundary. of the causal future of W. So we've got this sequence of causal paths to the p's, and the p's are approaching W. Sorry, the p's are approaching U. So in a globally hyperbolic space-time, an aspect of the compactness of spaces of causal paths is that if you take a sequence of causal paths to the p's, and the p's are approaching U, there will be a convergent subsequence, which is a causal path gamma from W to U. In other words, if we pick these paths to the p's at random, they may not converge, but they'll always have a subsequence that converges to a causal path from W to U. So the argument is very similar to the argument I gave at the beginning when we were discussing some aspects of the compactness of spaces of causal paths. This wouldn't be true in a non-globally hyperbolic spacetime because, for example, a point on this limiting path from U to W might be absent. It always takes global hyperbolicity to be able to say anything nice about compactness of spaces of causal paths. If U is really in the boundary of the future of W, the path gamma from W to U is prompt, because if it wasn't prompt, that meaning another one would reach the past of U, then a whole neighborhood of U would be in the future of W, and U wouldn't be in the boundary of the future. So I'm a little worried this might have seemed abstract, so I just want to give you an example. In Minkowski space, W could just be a point Q, and then the causal future is the future light cone in its interior, and the statement was that a point on the boundary of the causal future can be reached from Q by a prompt null geodesic, which was actually the first example I gave when we started discussing null geodesics. But that's true in this greater generality. Q could be replaced by any compact set in a globally hyperbolic spacetime, compact space-like set in a globally hyperbolic spacetime, and a point on its boundary of its future can always be reached by a prompt null geodesic. Now, there's another handy fact we need to know, which is that in general, a set C is called achronal if no pairs of points in C can be connected by a time-like path. Here it's important the path is time-like rather than null. So the boundary of the future of a set W is always achronal. Well, you see, let U be in the boundary, and suppose V is in the future of U. So this is a time-like path. Then we could reach V from W by a non-null path, namely the path to U followed by this time-like path. So since V can be reached by a path that isn't everywhere null, it's not in the boundary of the future of W. It's in the interior of the future. So the boundary of the future is always achronal. Because if U, as I said, if U is in the boundary and V is in the future of U, then V is in the interior of the future of W, not its boundary. So there's one more property of the future of a closed set, and then I think that's the last thing I'll try to explain today. The boundary of the future of a closed set is always a manifold without boundary, though it's often not smooth. In a globally hyperbolic spacetime, it's a closed submanifold. So here's an example, which is the future light cone of a point. So here I have to clarify one detail. We consider Q itself to be in its own future and also in the boundary of its future, another causal future. In other words, we allow the case of a prompt null geodesic that consists of only one point Q. Otherwise, we'd have to state too many exceptions. So with the understanding that Q is in J plus of Q, then the boundary of J plus of Q is the future light cone, including its vertex. And as you can see, that's a manifold, although it's not a smoothly embedded submanifold of space-time. It has a singularity at Q. So this is the general story for the boundary of the future of any set.
Can I ask you a question?
Yes?
What is a closed submanifold?
Well,
You didn't mean compact, like
compact. Well, a submanifold might be unclosed because you could remove a point from it. So closed submanifold is different from compact submanifold.
so
I think I
in the
meant-
sense of a closed subset.
Just means its complement is open.
Yes, I think, I hope I haven't made a slip in that closed submanifold is enough for the statements. Let's see the arguments, and that might jog our minds.
But they typically aren't compact,
Yeah,
right?
the one you drew is not compact, so it better not be compact.
Oh, sorry, W, sorry. I wanted W to be a closed
No,
submanifold.
but you said it is a closed submanifold.
Yeah, it's not compact, of course, but it's a closed submanifold.
In the sense of being
Yes.
a closed subset.
Yes.
Okay.
So, for the proof, pick an arbitrary point P in the boundary of the future. We want to show that the thing is a manifold near P. So you pick a small ball near P in which M can be approximated by Minkowski spacetime, and then you pick coordinates T and X centered at P. So here's a drawing in 2 dimensions. And in 2 dimensions, this drawing would really already be the proof. Remember that P is connected to W by a null geodesic. But in 2 dimensions, there only are 2 null geodesics through P. So this is one of them, let's say. And if that null geodesic goes to P, then everything to its future is in the interior of J positive W. And the geodesic itself is the boundary of J positive W near P. So the picture is already the proof in 2 dimensions. But assume we're above 2 dimensions. Then this picture, of course, is oversimplified because it is drawn as a 2-dimensional picture. So we pick a coordinate system near P in which M can be approximated by Minkowski spacetime. And we pick coordinates T and X such that P is at the origin. And now we look at the paths of constant X, straight lines in the T direction. So near P, the picture looks something like this. And a path of constant X, which I call gamma sub C, it's defined by X equals C, it's parameterized by the time. Well, if T is positive enough, keeping C fixed, it's in the future of P, so it's in the interior of J positive W. And if T is negative enough compared to C, it's in the past of P, so it's not in J positive W. So as you go forward in T, you go from not being in J positive W to being in J positive W. And that can only happen once. Because once you're in J positive W, any point in your future is certainly in J positive W. So there's a unique T for each C at which you enter J positive W, and that point is in the boundary of J positive W. So T is determined as a function of C by the condition of being in J positive W. So we can take C as local coordinates for the boundary of J positive W, and therefore the boundary of J positive W is a manifold, which we'll use tomorrow when we get to Penrose's singularity theorem and a lot of fun things about black holes. But I'll conclude with an exercise. In this exercise, you're supposed to consider different obvious sets, W, like a circle or a two-sphere embedded in Minkowski space in the obvious way. And you're supposed to figure out what is the boundary of the future of W. And you'll see, hopefully, that it's always topologically a manifold, though it's usually not smoothly embedded in spacetime. And I think we'll stop here. And the first topic next time will be the null Raychaudhuri equation, which you could call the Raychaudhuri-Sachs equation. Thank you. Any questions?
So you define focal points as kind of these first order variations of geodesics, but I could imagine a case where you have two non-distinct
Yeah.
paths.
The question of which we've had two previous versions of this question is, it has to do with the fact that non-existence of a focal point is a necessary condition for promptness, but not sufficient. There are obvious examples. An example in Lorentz Signature is a cylinder where a null geodesic could wrap around the sphere a lot of times. And if it wraps around the circle a lot of times, then it eventually stops being prompt, because for one thing, you could get there by a time-like path to the same destination. There are lots of other examples. But as three of you have asked by now, the absence of a focal point is a sufficient condition for promptness. A necessary condition for promptness, not sufficient. Any other questions? Yes?
When you said that sufficiently short null geodesics are prompt, when you say short, is it the arc length in space?
Well, you take a null geodesic. It has an affine parameter which has no natural normalization, but pick one. And then in that affine parameter, a sufficiently small bit is prompt. But more informally, take a geodesic and a point Q on it. There's a segment starting at Q, such that if you stop the geodesic anywhere in that segment, it'll be prompt. Sufficiently short really makes sense topologically. It doesn't matter how you measure it. You could pick any parameter at all along the path, and for a sufficiently small length, it will be prompt. I didn't give a formal proof, which we kind of will give tomorrow if we have time, because we'll need it eventually in discussing some of the later results. I don't know if we'll quite get time for it. But I thought it was an obvious result, so I didn't think we needed a formal proof today. Any other questions? Okay, then we'll take a break.